Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the Exascale Computing Project, ECP, of the United States Department of Energy. I'm Mosny Marcus from Lawrence Berkeley Lab, and I will be the host for today's webinar, Taking HACC into the Exascale Era, New Code Capabilities and Challenges. The webinar will be presented by Stefan Rangel. He's a member of the HACC development team. He joined the Computational Science CPS division at Argonne National Laboratory as an assistant computational scientist in 2021. And prior to that, he was a postdoctoral, also at the postdoc at Argonne as well, working on porting HACC's hydrodynamic solvers to the Aurora supercomputer. He began contributing to the HACC a while back while he was still a PhD at Northwestern University, where he worked on the design and implementation of scalable analysis software for any-body cosmological simulations. Esteban will receive questions through the Zoom chat and also Google Doc. I'll paste those addresses to the chat momentarily. I think we'll have breaks during his presentation so he can respond to the questions that come in. And with that, I'll stop my sharing here and take over, please. Stefan.
Okay, great. Thank you. Give me a second to start my screen sharing. Okay. I hope everybody can see my slides now. Yeah, so my name is Stefan Rangel, and I work on the HACC code as a computational scientist at Argonne. Sort of what is HACC? So HACC is a hardware accelerated cosmology code. And why do we run HACC? Well, one reason is to further theoretical research in cosmology to help understand large-scale structure of the universe, look for signs of new and interesting physics. And an important thing is to be able to compare with observations. So astronomical surveys, for example, like performed by LSST. An important part of that is to be able to create mock universes for helping survey design. And this helps provide theoretical models for summary statistics for data analysis. So emulators are work that comes that comes out of some of the cosmological simulations. And understanding data covariance parameters for estimation. And just so because we have one single universe, that means to be able to explore theory, we have to do forward modeling, and the simulations are doing the necessary forward modeling. So in this figure, we see the evolution of dark matter. So dark matter, as the universe expands, structure condenses, and from very smooth initial conditions. So in this panel on the left, upper left, we see this sort of very uniform, smooth initial conditions. And as the simulation evolves, we start to seeing this structure condensing, so clumping together of the dark matter, and you start to see these cosmic web, as it's known. Structures start forming, these filaments and these pockets of dense structures. So dark matter is a dominant mass component, and it's modeled effectively as a collisionless fluid. So perhaps the most fundamental structure we identify in simulations are something called halos. So these collections of particles, dark matter particles, form these overdense regions, and halos provide these deep gravitational wells where baryonic matter can collect, cool, condense, and eventually form the stars and galaxies that we see when we point our telescopes into the sky. So roughly half of the mass in the universe ends up in these dark matter halos by our current epoch. So by the time the universe gets to where we are now. And halos are identified in simulations by looking for these coherent structures, roughly about 100 times the background density. And in simulations, we use we use algorithms like DB-scan to be able to find these collections of particles. So another thing that is very important, so halos form in a process, in a hierarchical formation process. So another bit of interesting analysis that happens inside the simulation is tracking the evolution of these structures. So we want to understand how this colliding and merging happens, and we want to keep track of that. And that interaction history of halos is important because interactions between galaxies within halos can trigger epochs of star formation, and the total history of star formation can determine, for example, like the luminosity and colors of galaxies. And these interaction histories of halos are summarized in this figure, and so this is what we would call a merger tree. We also do something called core tracking, and here the very inner part of a halo, that's a very tightly bound set of core particles that's not easily disrupted, is being tracked as these mergers are occurring, right? So during this hierarchical formation process, we're identifying these cores and we're tracking them as the core of a halo merges with another halo. And what we're seeing on this figure on the right is the trajectory of all of the cores that eventually became one big massive object. And each one of those lines represents the trajectory of a set of core particles that was at one point an isolated individual halo. So this gives you sort of a picture of the kind of dynamical interactions that are happening between these overdense regions of particles and how they come together to form even more massive and even more massive halos as simulation evolves over time. And we use these core positions for several things, but an important reason to track them is they're likely good proxies for galaxy locations. So if one were doing some kind of modeling of galaxies and was interested in their distribution and placement, these core particles are good proxies for that. I think to note too is another bit of analysis or transformation really that happens in the simulation is these predictions of light cones. So in-body simulations operate in a co-moving gauge or in a co-moving coordinate system, but observations are not made in that same gauge. So because the speed of light is finite, we observe objects as they were when the light from those objects left them and are now are being collected as we see them now. So the effect is, when we look out into the sky, we see objects as they were at that time. So the farther away an object is, the further back in time we see it. So because HACC runs in these fixed size boxes with co-moving coordinates, we have to do some transformations to the data to make it look more like what observations ground or observations from telescopes would look like, and this makes the data from simulation much more useful for comparing with observational data. We do a similar kind of thing with these halos and merger trees that I had just described to you. So if we want to look at what a merger tree would look like, again, sort of in this frame of looking at it as an observer would, taking into account the speed of light, then we do a little bit more processing, and that's what this figure demonstrates: is how do we take something from a merger tree that's put together from a set of fixed simulation snapshots and and place that on a light cone, or how would we make those collections of objects that form the merger tree? How would that look from the perspective of an observer? So this is basically taking the merger tree information and taking the concept of a light cone and putting those two together. So very complex things happen in the simulations. And this is just a sort of a brief overview of the kinds of rich analysis, or the kinds of rich data that comes out of the analysis from the running n-body simulations, cosmological n-body simulations. I'll pause real quick here just to see if there are any questions, because I'm going to kind of change topics a little bit.
No, I think you can continue. Thank you.
Great. So I want to kind of change topics just a little bit and talk about HACC in the pre-Exascale era. So HACC was first designed and run at the very early petascale era. So its predecessor code was originally developed as this gravity-only cosmological n-body structure formation code written at Los Alamos, and was designed and run on the IBM Roadrunner supercomputer that featured the IBM Cell broadband engine. So from the very beginning, HACC was designed to work in a computing model that was expecting to have an accelerator, so a computing model with accelerators in mind. And to accomplish this, a principal part of the design is this notion of force splitting, where the force of gravity is split into a long-range component and a short-range component. A long-range component of gravity is calculated using this particle mesh method that uses a distributed memory Fourier transform-based Poisson solver implemented with MPI. So the long-range force is calculated basically using this distributed memory FFT implementation, and this is a part of the code that weak scales very well. The short-range component of gravity is calculated using this direct particle-particle comparison, and it's implemented with C intrinsics or whatever programming model accelerated for the accelerator is available. And for the cell, this was C intrinsics, but the way to think about it is the short range force component of gravity takes advantage of the accelerator. So just a sort of more fine-grained picture of what's happening with force splitting. And the reason gravity really is difficult is because it's infinite and unshielded. So in an n-body simulation running on a modern supercomputer, the domain decomposition is such that we have subvolumes of particles, but that means each particle is interacting with every other particle on every other rank in principle, or on every other part of the supercomputer. So that makes it difficult, but the separation of scales for the forces is really the key to getting good scalability. So to achieve this, to be able to incorporate or separate long range and short range, we implement a technique of operator splitting. So this is a kind of leapfrog integrator. And we use basically a symplectic integration scheme that uses a kick-stream combination. So either kick-stream kick or stream kick-stream. But the principle of symplectic integration is the central component of this. And the spectral force handover technology is really the important sort of engineering part of this, where being able to stitch together this long-range force and short-range force is something where a lot of sort of thoughtful planning has to go into this. We use a low-order cloud-in-cell CIC deposit scheme, and there's a spectral shaping that reduces noise to do this stitching together. And the handover is extremely compact. So this is pretty important part of this. And basically 3 grid units in length for the handover. So using this kind of design, now that we have this force splitting technique, this allows HACC, I just kind of alluded to, use a domain decomposition where the large volume of the simulation can be partitioned into these smaller subvolumes. An important part of this domain decomposition is this concept of overloading between MPI ranks. So each rank has a thin shell of particles from its immediate neighbor. And this helps cut down on the amount of communication time between adjacent MPI ranks. So no particles need to be exchanged during the subcycles. So the subcycling is for the short range force calculation. And particles are refreshed or cached periodically. And the figure on the right here demonstrates sort of the typical time step where we take a large PM step. So here we're using the spectral solver to solve between T1 and T2, but then we take a lot of smaller fine-grained time steps that are the subcycles for calculating the short-range force. And these are done, like I said, using the accelerator. So in preparing for Exascale, there's several challenges. One is just more that there's a large increase in the compute capabilities and more increase in the compute capabilities and in the available memory. So if we just look at, say, Summit to Frontier, we see about 8 times more flops available on the systems, but maybe only about 3 times more memory. And these Exascale systems also have multiple programming models, different kinds of accelerators, different kinds of frameworks available. So just from a code development standpoint, there are multiple of these programming models to choose from. And the CPU analysis routines, especially on the host, so I pointed to HACC is not only an n-body solver for gravity, but also has a large amount of analysis routines. And these analysis routines traditionally done on the host become a larger fraction of this overall execution time. So one thing is, what do we do with when we have a lot more flops, but maybe not as much available memory? So we turn to add additional baryonic physics to the gravity only solver. So we developed this this version of HACC we call CRK HACC, where CRK is this conservative reproducing kernel formulation of smooth particle hydrodynamics. So it's engineered developed by one of the HACC team members, and it's a general SPH reformulation that has more accurate error control. And it resolves some of the discrepancies with the grid-based hydrodynamic schemes. We can run non-radiative hydrodynamics, and we also have the ability to run subgrid models for radiative cooling, star formation, supernovae, and HN, so active galactic nuclei. So these are some of the new code capabilities that are that have been put into HACC that are now can exploit some of this additional flops available with exascale supercomputers. I'd like to just mention some of our software technology partners in ECP, and some of these collaborators have been really important for us to work with. I'd first say the ArborX team that have a very fast GPU accelerated geometric search library. This was real important for us to be able to accelerate some of the analysis routines, for example, using the Friends of Friends Halo Finder so that the halos that I pointed to earlier. And for the AGN center finding, important for subgrid models, and a different kind of halo finding we do called spherical overdensity halo finding. So all of these were accelerated with the ArborX library that has a portable backend, but is built on top of Cocos. We also work with Veloce and SE projects to implement low overhead checkpointing, low overhead checkpoint restart, and being able to do compression for some of our data analysis outputs. And these, so SE is a lossy comparison scheme, and where we can work to create errors that they're bound and controlled and acceptable for the analysis that we're trying to perform. And we've worked with the Alpine team for visualization. So preparing for Aurora. So the prime, so in the Exascale, so as we've sort of entered Exascale, you know, and we've had systems like Perlmutter and Frontier, and finally Aurora, the deployment has come, you know, on different schedules. And the primary and ongoing development of CRK HACC has been using CUDA, with support for HIP sort of automatically happening in the code. I'll talk about in just a second, through macro transformations. And we chose SYCL to use as the programming model for programming HACC for Aurora. So HACC supports multiple build implementations, as it has historically, and to exploit the low-level programming model features and get the very best possible performance on whatever target system that is. And we've had a pretty long history of doing this as we've run on nearly every supercomputer since Roadrunner, using whatever the best programming model is to tune kernels for those architectures. So to run on Aurora, we're using this semi-automated migration pipeline, this to transform CUDA to SYCL. And we started off with the CUDA kernels. We use Intel's tool called Cyclomatic. This is a migration tool that has a lot of capabilities. We're using it in a simple way where we're migrating individual kernels at a time. And we're using, in addition to Cyclomatic, we developed our own tool that is a Clang-based libclang tooling tool to do functor transformation. So CUDA device kernels are transformed by Cyclomatic into SYCL device kernels, and these are SYCL device functions, and we want to turn those functions into functor objects. And there's several benefits for doing that, but for us, it was a lot easier to have a wrapper that can call both CUDA and SYCL in the same form, because that wrapper sort of relied on being able to call the function by name. And this purple box here kind of shows the code organization inside CRK HACC. An important thing that we did, and the reason we need this functor tool, is we've written GPU API wrappers. So inside HACC, inside the code base, instead of calling something like CUDA memset, we'll call a sort of generic wrapper kernel or wrapper invocation that would say something like invoke GPU memset, and we would have different build implementations for the CUDA version, SYCL version, and perhaps any other programming model that we want to support, making the host site code a lot more agnostic to whatever the accelerator programming model is. So in order to accomplish that, an important piece of this whole process was transforming our SYCL device functions into these SYCL functor objects. Another important thing for supporting rapid prototyping and development, especially we've had a partnership with Intel, working with the Intel engineers, is developing a testing framework or a testing harness where using a lot of the same code that comes out of HACC, we can execute kernels, individual kernels from the solver on their own. So basically, we can have an executable that's capable of executing the individual kernels from the solver. And the way that that works is that we run HACC basically in a mode where it can take snapshots of the GPU data and save those for later use by the testing harness. And when we run this testing harness, we can load up those snapshots from taken anywhere during the simulation, run the kernel in isolation, and even test the output of the kernel. So if the kernel was modified for performance reasons, this testing harness allows us to even validate that the modifications made were correct or produce the correct result. So this was a very important tool that was very useful in all of this optimization process. I'd like to just show a quick movie of an adiabatic simulation. And this was developed on the code was run on Sunspot, which is the Aurora test and development system at Argonne. And this just shows you the sort of the additional physics that's going on inside this these new capabilities that we've added to HACC. So what we're seeing on the left is the gas temperature, and gas temperature is going to increase inside these clumpy regions where there's more hydrodynamic physics involved. There's more hydrodynamic interactions happening. And on the right, we're seeing the dark matter velocity magnitudes. So inside these tight regions, these are the halos of the simulation. There's more there's more virial interaction. So particles are moving around faster and interacting more and generating more heat for these particles. So this is sort of a just a visualization of the new physics that we've been able to integrate. I'll pause again quickly here just for more any more questions.
There is one question here. Is the CUDA to SQL migration fully automatic with Cyclomatic and the SQL functor Clang tool, or do you still need to go in and tweak individual functions by hand?
So it is very, very middle. So the answer is no, but it is, I would say, 98% automatic. There's still some, there's a few corner cases that are correctly handled by Cyclomatic, but our functor tool doesn't resolve automatically. Template specialization initialization is one of those things. I mean, it's kind of an esoteric topic, I guess, but so there are some particular transformations that we need to do in our SQL functor tool that are just maybe we just don't know the right libclang tooling, AST type of syntax. But for the large part, I would say about 98%, I would say yes.
Okay, thank you. Continue, please.
So now I just want to point out a paper that we recently published. So this is to appear in P3HPC workshop as part of SC23. So I just talked about, there's a lot of additional physics and complexity that's going into HACC, and we're maintaining separate implementations of CUDA and HIP and SQL, and obviously, this is not ideal, but prompted us to sort of start this performance portability productivity study using SQL. So this work is, like I mentioned, going to appear in the P3HPC workshop, and the rest of this talk is a kind of a preview those results. And of course, I join you to encourage you to join us at P3HPC if you like the material presented here, because the workshop is centered on all of these topics. So as an experimental setup, we started off with an adiabatic simulation of 512 cubed particles, the 2 times there because we have dark matter and baryons. We're taking 5 time steps with 4 fixed subcycles. This uses 8 MPI ranks. We use 4 GPUs to do this. On Aurora, there are 6 GPUs. We're using 4 of those just to maintain parity with all of the other systems. On Aurora, this means 1 rank per tile because each GPU has 2 tiles. On Polaris, we're using 2 ranks per GPU because the A100 that we used isn't in a tile structure, and we know that by doing so, this results in about an 11% lower efficiency, but just so we'll take that into account when we do our analysis. And on Frontier, we're using 1 rank per GCD, and again, this is one node of Frontier. And the systems are Aurora, Polaris, and Frontier, and where each of them is a GPU accelerated system with different computational capabilities. On Aurora, this is the Intel Data Center Max GPU, the A100 on Polaris, and the on AMD it's the MI250X. So initial results, right? So because we have HIP versions, CUDA versions, and SYCL versions, and SYCL is a portable programming language, we want to be able to see how does our SYCL implementation compare to the native implementations on the systems. So HIP on Frontier, CUDA on Polaris. And the first thing in our comparison we noticed is that fast mass optimizations weren't enabled by default on all the compilers, and this manifested first by seeing that the implementation that we had in SYCL seemed to be much faster than the native implementation. I think what we did on Polaris was we looked at the generated PTX, and the first thing that jumped out at us was the fact that the math functions were the approximate math functions, and we finally sort of realized that the fast math optimizations were not enabled by default. So anyway, enabling fast math on Frontier and Polaris then brought our times back to much more comparable timings with SYCL, which was good. It's actually beyond our expectation that SYCL would perform at near parity with the same optimization settings on these systems. But the first version, our directly ported version from CUDA to SYCL on Aurora was not very fast, or comparably not as performant, and that prompted us to do a lot of performance optimization. And I'll talk about those optimizations in the coming couple slides. So what optimizations did we do to the GPU solver kernels? And first thing we did was identify the hotspot kernels. These are geometry, corrections, extras, acceleration, energy. All of these are hydro kernels, adiabatic hydro kernels in CRK-HACC. The important thing to, I guess, note is that the algorithmic implementation of all of these kernels is what we call a half-warp algorithm. So the thing to take away here is that particles need to interact with each other, and particles are grouped into are partitioned using a tree data structure, but the leaves of the tree are these fat leaves that we call, where the leaves contain some fixed number of particles within them. And then the code, we identify which leaves need to interact with each other, and the total amount of work then done by the accelerator is going to be doing all of these leaf pair interactions for all of the leaf pair set that we identify. The way this looks on the GPU is so either for a warp or a wavefront or a subgroup for the Intel architecture is that we have some number of lanes, and half of those lanes are dedicated towards loading particles from some leaf A, and half the lanes will interact or will be loaded with particles from some leaf B. And then the idea is to do particle interactions between lanes of the single either warp or yeah, subgroup size or subgroup on different architectures. So part of these optimization, or one of the largest that we focused on, was optimizing cross-lane communication. And here we're talking about the data sharing that needs to happen between lanes. And what we're seeing here is sort of one instance of this total, leaf A size cross leaf B size divided by warp size. If you did this, you'd see that you'd need exactly this many instances. And the important part of this particular type of communication, or constraint on it, is that there's a pairwise symmetry that's defined in these equations for the hydro equations. And so this is critically important for the correctness. And that by pairwise symmetry, I mean that if some lane I is interacting with some lane J, then at that same time, at that same instance, that same lane J needs to interact with the same particle I. So if we impose this pairwise symmetry constraint, it's a particular kind of communication. That communication is captured by an XOR-based shuffle pattern, and in CUDA we call this intrinsic, the shuffle intrinsic, and the corresponding group function on the Intel architecture using SYCL will be something like select from group. Here I just on the left, this is a bit getting into the weeds, but I'm showing assembly snippet for different select from group code generations that come under different circumstances, depending on how this is used algorithmically. But the thing to take away here is the top code snippet uses a type of register access called indirect register access, where special registers, these A registers, address registers, are used to reference parts of the register file. And this is a very slow, this gets executed very slowly. One access per cycle, what ends up happening. And below is a more performant way of doing of accessing data from the registers called register regioning. So to explore sort of different communication strategies, we looked at using shared local memory, where this is a rather trivial thing to do, but where we create a shared local memory available to the work group on the GPU, and all of the data exchanges between lanes are basically going through a shared local dedicated memory for those exchanges. With Intel and our partners at the Intel engineers coming through the Center of Excellence at Argonne and Intel, we explored restructuring some of these loops, basically so that the code generation would look like this more performant code on the bottom. And then we also explored using these optimized instruction sequences, so basically writing inline assembly to do the exact data exchanges that we wanted. And I just want to note that for the broadcast version, this required pretty significant restructuring of the loops. So this breaks the notion of basically being able to use cyclomatic, because the transformation needed to do these broadcasts are almost rewriting the kernel or significantly restructuring the kernel. So this is so the question, addressing how how much comes directly from cyclomatics. So using these broadcast version, not very much at all. These are pretty much hand-tuned. I'll quickly go over here for time, but this is basically the inline assembly version of what we did. I showed you the way this half warp algorithm works is half the particles are from one leaf, half are from another. After some staring at the pattern, we realized that essentially, if we could do these cyclic shifts on half the warp size or half the subgroup size, we could achieve the same kind of communication pattern. And this basically can efficiently be done with 4 move instructions of inline assembly. Exactly the way that looks in register space is something like this. I'm not going to spend a long time on this, but if anybody's interested in this particular, feel free to reach out. So I just want to talk now just some of the optimization results. So for the hotspot kernels, so these are like I mentioned, the acceleration, energy, XRS corrections, and geometry kernels. So on Aurora, on the Intel Max GPU Max, the most performant implementation was the broadcast implementation. On almost all kernels, I think on some the VISA version is still very good. And the largest differences between the broadcast versions are in these extras and corrections kernels. And the difference here, the reason why we're seeing this biggest difference is because the loop restructuring not only allows us to use these broadcasts with more efficient code generation, but also lets us reduce the total number of atomic instructions that are needed. And this extras and corrections kernels are very heavily used atomics. So as such, the difference here is more of a reflection of the cost of atomics than it is of the communication between lanes. On Polaris and Frontier, the results are almost quite the opposite. The broadcast version, which was most performant on Aurora, on the Intel GPU, is actually the least performant. So looking at Polaris, looking at the A100, the broadcast version actually performed most poorly. And the reason is that the broadcast version uses a lot of registers. The initial development of this half-warp algorithm was to reduce the number of registers needed, and this broadcast version, being very register heavy, is sacrificing performance here because of its excessive register usage. The select from group version that was sort of least performant, I didn't really point that out, but it was least performant on Aurora, is now the most performant. And like I said, and the shuffle intrinsic and the select from group are analogous to each other. So the code generation for select from group is closer to, at least from the communication standpoint, closer to the native HIP and CUDA implementations. The memory versions of the SLM memory versions that were also pretty good on Aurora are also pretty good on Frontier and not quite as good on Polaris. And the reason behind that is that the memory version, the shared local memory, and the L1 cache on the A100 share the same memory hierarchy on the GPU. So basically, the more shared memory that we use, the less L1 cache, the less memory we have in the L1 cache. So any kernel like DUDT and acceleration, or the energy and acceleration kernels that are very register heavy and will have register spills, will be able to least take advantage of the L1 cache, and the L1 cache is important for register spilling. So now I just want to talk about the performance portability analysis. And so we have this metric for defining performance portability. So this PP metric, where A is an application, P is a specific input, and H is a set of platforms of interest. And the efficiency is this metric on AMP. And important to note that the application efficiency is calculated relative to a hypothetical application that's able to use the best version of each kernel on every platform. And so this application efficiency graph is looking at it's a cascade plot, and the cascade plot, the way to read this is that for each one of these lines on these plots on the graph, there's a different labeling. So the cascade plot is always going to be monotonically decreasing in efficiency, and what's important to see is sort of the rate of decrease. So we could see, for example, the sickle broadcast version, it was most performant on Aurora. So give the first label is C. It was less performant on Frontier and worst performant on Polaris, indicated by the label ordering. And you could see the steep drop off for sickle broadcast. The most efficient, and what you see by sort of the flattest line is our sickle select plus VISA, and what this means here is we're using the select from group version on Frontier and Polaris, and the VISA version on Aurora. And here that has a application efficiency in this cascade chart that is the highest and most flat. And if we want to look at the performance portability, so this is this bar chart, performance portability on using this metric, the highest performance portability was achieved by this select plus VISA. Now, a thing to note here is that performance portability doesn't incorporate a productivity metric. So the cost of maintaining the different code bases. So performance portability here assumes that or allows for, without penalty, different code paths, so different build configurations for the different target systems. So there isn't a penalty for having code paths that are wildly different from each other. And that's really captured with this productivity analysis. So with this metric of code divergence. So with code divergence, now we can look at, using this metric, we could look at how much code is, how much divergence there is between the code base, where this distance represents the distance between the source code required to solve problem P using application A on platform side J. But this gives you, this is kind of like a pairwise distance metric on the code base, on the differences in lines on the code base. And this navigation chart shows us the way to, I guess the way to read this is we have performance portability in terms of application efficiency on the vertical axis, and then the code convergence on the horizontal axis. And the fact that all of these different implementations are near one on the vertical means that for all of the implementations that we have, for all of the specializations that we did, they were very finely done. So there's, out of thousands of lines of code that make up all of the kernels, the differences between all of these specializations that we did for improving the communication cost were at most, I think the VISA version is at most 200 lines of code. The shared local memory version is something like only 20 to 30 lines of code. So all of the implementations that we have are not very different from each other in the grand scheme of things. What we have, this sort of outlier that we have here, this unified, basically is assuming that we're using CUDA, that we have two variants of the code. So CUDA for HIP, CUDA for the A100 on Polaris, and HIP for Frontier, and SICKLE for Aurora, and basically the unified means we have different code versions specific to all of those. So that's why it's an outlier. But all of these are the SICKLE implementations, and that's why you see them all lined up with minimal code divergence. So here, this select plus VISA, it turns out to be the highest ranking in this navigation chart, being that the performance achieved and the amount of divergence is in a combined way minimal. And that's the last slide I have here. I'll pause again just quickly for questions.
There is one here. Esteban, you mentioned the distributed FFTs only briefly. What size are they, and about what about and about what fraction of the overall execution time do they take?
So that part of the code is the part of the code that almost perfectly weak scales. But the question about how big do they go? I mean, well, on a large run, I mean, that could be 10,000 or greater FFT size, right? So 10,000 cube or even larger. This really is kind of a parameter that there's a function of the simulation's resolution and overall volume, but it in excess of 10,000 is not uncommon for large scale runs. How much as a fraction of the overall execution time, again, is also a function of sort of the resolution and particular configuration for the simulation that we have. I mean, just kind of roughly ballpark number, I would say it's less than 20%. But again, this kind of depends on exactly the resolution that we're aiming for, and available memory, and how big we want to make the FFT itself.
Okay, you have a final slide or?
Yes, so just some disclaimers for the numbers that I wanted to show, and conclusion. So HACC introduced these new physics into the simulation, mostly because of the increase in computing power available now for Exascale. We described this process of maintaining a CUDA code base and a SICKLE code base, and how to migrate between them. We identified shuffles as being something that wasn't performance portable from NVIDIA GPUs to the Intel GPUs. We developed sort of very straightforward workaround. I think the shuffle implementation with shared local memory is something is probably broadly useful to many developers. And we've demonstrated through this practical potential for writing performance portable applications with SICKLE, and almost with a very high performance portability score, near zero code divergence, and the pure SICKLE version is also very high, 0.91. So it's just some key takeaways from this whole going to Exascale. Code outside of our solvers, so some of the in situ analysis is becoming a bottleneck, or had become a bottleneck, and sort of emphasize the need for us to GPU accelerate those. This was some of the partnerships that, like I said, we've done with ArborX, where we're using performance portable GPU accelerated libraries to achieve that kind of speed up needed with GPUs, and also get some portability and expertise from their team doing these kinds of geometric searches. This is really important. And just overall, even from the core code capability of solvers, this increased code complexity makes maintaining multiple implementations more burdensome, and it really highlights the need for performance portable programming models. The sickle version of HACC, we think is an exciting proof of concept of having a single programming model that can be used across different GPU architectures without sacrificing performance. And these kinds of performance portable programming models and standardized programming models we're really strong advocates for. So thank you for inviting me, and thank everybody for attending in their time. And yeah, any last questions I'd like to take?
Thank you, Stefan. I'd like to invite the participants to unmute and ask questions directly to Stefan, if any questions.
Hey, this is Miro from Oak Ridge. Can you guys hear me?
Yes.
Sure. Yes.
I have a question about the FFT actually. How is your data distributed across the MPI ranks? Are you using like a box layout or pencil layout? And once you do for the input when you start the transformation, and also at the end of the transformation as well?
The input at the beginning of the transformation is a regular grid subvolume decomposition, but the FFT itself is done using the pencil layout. And
the final configuration is still pencil.
After we perform the FFTs using pencil distributions and FFTs, the FFT on the pencils, and the final redistribution is back to grid.
Back to grid.
Yeah. There's several. I think we have if you're very interested in this, there's a standalone ECP proxy app we have called Swift, SWFFT. And this encapsulates all of our FFT code into a standalone code you can download and try, that I think runs on most major systems.
Thank you.
And there's a lot of description as to how it works.
Thank you.
Sure.
Any further questions? If not, thank you again, Stefan. Thank you all for joining us today.
Great. Thank you.